Yeah, Megan.
So if the problem says that like it is ordinary addition and then it gives you like a different rule for multiplication, does that mean like it won't, is there like a rule that it won't break any of the addition axioms, or do you still have to worry about the addition axiom?
No, if it's ordinary addition, so you've already proved that the those axioms are satisfied for ordinary addition, then yeah, you don't have to worry about those parts.
Okay. Okay.
Now, if it says ordinary scalar multiplication, but the addition changed, then you still would have to worry about 7 and 8 because those have addition in them.
Okay.
So you can't just skip all the ones with scalar multiplication in that case, because there are some that have addition in it. But yeah, if it says ordinary addition, you don't have to worry about the addition ones.
So it's just knowing that.
Yeah.
It'll make it go faster.
Go next to go faster, yeah.
And then are we gonna do more examples of this stuff?
Yep. Sorry, we're ready today. Yep. We're ready to those today. Other questions at all?
Yeah, I guess so. Just can you, when we're showing this zero vector, do we do that the negative u or -1 times u, or equals the additive identity? So u plus -1 times.
That's not negative. That's not -1 times u. That's u plus the negative of u. It's how you're defining the inverse in that case.
Yeah. So that's okay.
In order for it to be a vector space, I'm sorry. If you know that you have a vector space, then that other theorem has to hold.
Yeah.
Right. But that's not what you're doing for this. You just need to identify relative to the zero vector that you found for axiom 4. What's the added inverse? Bless you. So in whichever one that you were asking me about, I know you emailed me over the weekend. Was it the one with major C's? Is that right?
Yeah.
So since it's ordinary addition, what does your additive inverse have to be with ordinary addition?
Just the negatives.
Okay. So what will happen is that you'll get issues when you try to do, I believe it's 7. Actually, it's 7
Is
causes
that
the
the
problem.
closure of scalar multiplication?
That's 6. The closure of scalar multiplication is okay. It still fits the form that you're supposed to get. 7 is the issues with the distributed over vector addition.
Oh, I see.
That's the one that's going to have cause issues.
I'm just going off this theorem 5.1.1c. What it says that.
Well, I know where you're at. Yeah. So if it is a vector space, then it has to satisfy that. So you could say that relative to the zero vector, I know my inverse has to be this, but according to the theorem, I'm supposed to get this, and they don't equal each other, so I know it's not be a vector space. That also works as an argument to say that's not a vector space. The reasoning behind why it doesn't work is because of that distributivity issue.
Yeah.
When you have the distributive property, it doesn't distribute properly with the way that particular scalar multiplication is defined. Forgot the word that I was trying to get to. Yeah, Megan.
So for the homework in general, do we need to show all of our work for each axiom, or can we like? Just
I would do it for practice,
because like.
so that you practice going through each of the axioms. I know it says determine whether or not it is. So if on the exam you know for certain that it does, what particular one doesn't work, you can just do that one. But for this, I think practicing doing them all is helpful as far as preparing for the exam.
Okay.
Is what I would think. That would be my suggestion.
Okay.
Also, it helps for partial credit if you did do something incorrectly. That's also true on the test. I just think it's good practice to go through all of them, even because it's also good practice to see when it fails. Not only when it holds, but when it fails. I just think it's good practice to go through all of them and see what happens. That's my opinion. Other questions? All right, well, let's talk more about subspace then. So remember, for subspace, we start with a vector space V. So we already know that the addition and scalar multiplication on V satisfies all 10 axioms for being a vector space. We're taking a collection of vectors inside of V, so W is a subset of V. Then W is a subspace of V if and only if W is itself a vector space under the exact same operations as V. So that was our definition of subspace. So notice again, we've got lots of structure already. We know that V is a vector space. So we know that whenever I take vectors from V and any scalars that I want, I know that I satisfy all 10 of the axioms without any question. So that means that when I take vectors from W and do operations, they have to satisfy the same the same axioms that they would have in V. So for example, if I take two vectors from W, if I add them together, the order doesn't matter in which we add them. If I take two vectors from W and multiply a scalar times the sum of those two vectors, I know it still distributes because they distribute in V, so they have to distribute in W. Because the vectors in W are also vectors in V. What we have to worry about is the closure idea. I know that when I operate two vectors together in V, add them together, it lands back in V. What I don't know to start with let's try that again. What I don't know is if I start with two vectors in W and add them together, I land back in W. I know that when I take two vectors in W and add them together, they have to land back in V, because V is a vector space. We're trying to see if I have a smaller piece of it that also ends up being true. Is it also a vector space? So subspace idea. All right? So what we proved last time was that the theorem was that W is a subspace of V if and only if W is closed under addition and scalar multiplication. That's all we have to check. All right, so let's look at this vector space practice sheet that I handed you last time. Did I not get one of those sheets last time? The subspace practice one. Yeah. I did. Vector space practice. There it is, subspace practice. Trying to find one. All right. Let's look at the second one. So, in number 2, on that practice sheet, we're given that V is the set of all continuous functions on the interval from A to B. So, you might see this notation like this, where there's a C in front of it, and then brackets AB. So this stands for set of continuous functions, actually continuous, what we say, real valued functions on the interval from A to B. All that means is that real value just means that the outputs that you get from the function are real numbers. It's all real valued function meaning. Some people put a superscripted 0 on here as well, because when you start upping the superscript by 1, 2, 3, and so on, it tells you how many times the function is differentiable. So if you did C1, it would be the set of differentiable functions on the interval from A to B. And C2 would be the set of twice differentiable functions on A, B, and so on down the line. I'm not so worried about the notation. Anyway, but they're telling you that this is a vector space. And what we mean is that as long as we do regular old function addition and regular old scalar times a function, those satisfy all 10 axioms. Okay? So what W says is I want the set of all F, and just to be specific, I want the set of all F and V such that if I integrate over the interval from A to B, I get 0. And we want to see whether or not this is a subspace. Just as a little bit of review of calculus, I don't have any definition issues for W here. Every single continuous function is integrable from A to B. I don't have any issues with the integral existing. You've been through Calc 2. You've talked about improper integrals, for instance, and you've talked about ways that functions may not have an integral on a particular value. That wouldn't work in this case because I said it was a set of continuous real valued functions, and I wouldn't have an improper integral in this case. But I do know, and you should also know, that if I have a continuous function, then I can also take its integral. Not any issues. There aren't any issues here. So I don't have, for what I'm saying here is W is not empty. There are functions that have a 0 integral here. All right. So for the proof of whether or not W is a subspace, we're going to let's let two functions be in W, and we'll just talk about a scalar. So I'll call it C, B, and R. According to the theorem, it says that we can test whether or not W is a subspace simply by showing that W is closed under the operation. What I mean is that for addition, we need to show that F plus G is also back in W. That's what closure means, right? If we start with two things in W and add them together, it has to land back in W. That's what closure means. Now, what's our defining characteristic for being in W? How is W defined here? Okay, so the integral of the function that we're worried about from A to B is 0, correct? So what is it we want to show if we're going to show that F plus G is in W?
The integral from A to B of F plus G.
Okay, so if we want to show that F plus G is in W, we want to show that the integral from A to B of F plus G of X is also equal to 0, right? This is the defining characteristic for being in W. When I integrate the function, I get 0. Integrate the function over the interval, I get 0. Right? So to show this, I really need to show this. Does that make sense? Okay. All right, so let's do that. Now I purposefully wrote this as F plus G of X, just to remind ourselves of how we define function addition. What is F plus G of X equal to? Good. And now what do we know about the way the integral behaves with respect to addition?
We can break it up.
Yeah, we can break it into two pieces, right? So we can break this up as integral of f of x plus the integral of g of x. And what are we assuming about f and g? Where do they live? In W, right? Both f and g live in W. So what must be true about both of these integrals? They both have to be 0. And certainly 0 plus 0 is 0. So where does that tell us f plus g lives? In W. Good. We showed that f plus g satisfies the characteristic that it needs to satisfy in order to be in W. That makes sense? So this is closure under addition for this one, so we're halfway home. Let's do scalar multiplication. What do we need to show for scalar multiplication relative to this problem? Let's actually put it in context. What do we need to show with respect to this problem? What do we need to show? Okay, so I multiply the function by the scalar, it's still in W, and what's the defining characteristic for being in W again? The integral 0, right? So we need to show that the integral from a to b of CF of x dx is 0, right? This is context specific to this problem, right? This is how you get into W. You integrate the function over the interval from a to b, you get 0. That's how you get membership into W. Right? If you don't have that ID card, they won't let you into the door. Right? Okay. So this is how we define our, well, this is just a notation for how the scalar multiplication of the function would be. So scalar times the function, when we integrate it, we still have to get 0. But how is scalar multiplication defined for a function? How is CF of x defined? Good, yeah, that's exactly right. That's how it's defined, right? Remember, when we do function addition or function scalar multiplication, it's defined on the outputs, correct? That's why f plus g of x was defined as f of x plus g of x. It's defined on the outputs. Same thing here, right? C times f of x is c times f of x. Now, again, we've got integral. So what can I do with this constant with respect to the integral? We can pull it out in front. And then where does f live? In W. So what's this integral have to be? 0. So we have c times 0, and c times 0 is still 0. Good news is we're still in the real numbers. Into some other algebraic structure. Maybe it's not 0 anymore. One of the rings that I do ring theory. That's what I do is research. And one of the rings I worked with in my dissertation, 1 times 1 was 2. So fun stuff. That particular ring didn't have a multiplicative identity, obviously, since 1 times 1 was not 1 anymore. So math gets weird. Anyway, so what does this say? Where does this tell us about the constant times the function? Where does it live? It lives in W. So are both the closure axioms satisfied? Yes. So we have that W here is a subspace of V. Now, there was something special here about being 0 that the integral came out to be. Would this have worked if the integral was 1 for a function? If that was the definition. No, because in particular for addition, when you take f plus g, what answer would you get for the integral? 2, right?
Thanks for giving us the answer for 4B on the homework.
Oh, well, good. I don't know what 4B on homework was, so.
Integral.
Oh, okay. Well, then you'll know how to check it. All right.
So is this the same process that we go through for every subspace? We only check the addition with scalar multiplication?
Yep. First, to check if it's a subspace, because you're already assuming the bigger space is a vector space.
Okay.
Is it okay? Okay.
This is easier than vector space.
I
only have to check 2.
I would agree with you. It's easier than vector space because you only have to check 2. It's less tedious. Yes, I agree. All right, so let's talk about some specific notation that we might see for particular vector spaces, and then to do a couple more examples here with subspaces. So we already saw continuous functions on the interval from a to b. We did c of a, b, and I talked a little bit about what if you want a differentiable. Other ones that pop up, of course, are your Rn, for example. So this is just your set of all n tuples. We've seen that. We've actually written that down. Another one you'll see, oops, it's not that. You'll see a P sub n. This is the set of all polynomials with degree less than or equal to n. And I have to be a little bit careful. I have to say along with the 0 polynomial. Remember that the degree of a polynomial is the highest power of x that you see in the polynomial. So constant polynomials, I should say non-zero constant polynomials, have degree 0. However, the 0 polynomial doesn't have a degree. Because I can't tell if it's 0, I can't tell if it's 0x squared, I can't tell if it's 0x to the 757th power. I can't tell what the degree of the 0 polynomial is. It's not well defined. So the 0 polynomial doesn't have a degree, which is why I have to put that extra addendum in there. From a set notation perspective, I could write it this way. This would be the set of all, write it this way, I equals 1 to n of a sub I, x to the I, such that a sub I is a real number. That works. That gives me the set of all polynomials that I want because I'm allowed to put zeros in where I want to. Another notation that pops up that you'll see is capital M with subscripts m and n. And this is a set of matrices that have dimension m by n. I'm only mentioning these because you'll see the notation pop up from time to time. I want to do an example with P sub n here with a subspace. So as far as the example here is, let's let V equal P3 and W be the set of all little p in capital V such that the degree
of P of X actually is 3.
Notice that the definition of P sub n is degree less than or equal to n, not just equal to n. So this W actually is a piece of V and not all of V. Because V would contain all your cubics, but it would also contain all your quadratics and all your linears and all your constants. This only contains cubics. Right? So the degree has to be 3. So I don't allow a 0 in front of my x cubed term, if you will. All right, so the question is W a subspace? So again, for subspace, we need to show, is it closed under addition? Is it closed under scalar multiplication? So let's think about addition first. If I take two polynomials that are degree 3, do I get a polynomial that is degree 3 back again? Let me ask again. If I take two polynomials that have degree 3, do I necessarily get a polynomial that has degree 3 back again? Okay, maybe not. Okay, let's think about if I can come up with a counter example.
N cubed plus negative N cubed.
Okay, so yeah, well, let's say we, as an example here, say we take x cubed and take negative x cubed plus 1 even if you want. Don't worry about 0. What happens when you add f of x and g of x together here? What do you get? Or I get 1, yes, I do. I thought I was going to have to subtract, but I would put the negative on there. So what's the degree? What is the degree of f plus g here? 0. So what does that tell you about f plus g? Is it NW? No. Right. So we have a counter example here, right? I've got two things that start off, and certainly f and g are both NW, aren't they? But when I added them together, they're no longer in W. So W is not a subspace. It also is not closed under scalar multiplication because there's a specific scalar that wouldn't work. What specific scalar could we show that it's not closed under scalar multiplication? 0, yeah. Okay. So just write the conclusion here. W is not a subspace of V, since W is not closed under addition. So when you're trying to prove something as a subspace, if it is a subspace, you have to show it's true no matter what pieces, what vectors you pull out of it. However, to show that it's not a subspace, you just need to find a specific counter example that does not work. It shows that the operation is not closed. So that's why I got to pick two pieces here. That makes sense? Okay with that? All right. There's a specific type of subspace that pops up when doing vector spaces that we're going to be concentrating on in the next several sections, and that's the idea of span. Before I get to span, though, I need to give you a definition.
Is this a different section?
It's in the same section. It's still in 5.2. Okay. It's a good question, though. It seems like I'm going on to a new section, but I'm not. This is the same section. All right, so let's let x1, x2, out to xn be in a vector space. Like I mentioned last time, if I use the letter V, assume it means I'm talking about a vector space unless I'm specifically asking you to show it is a vector space. Okay. So if you see the capital letter V, you can assume that I'm talking about a vector space to start with, unless I specifically say show that V is a vector space. Then I mean that I don't want you to assume it to start with, otherwise there wouldn't be anything to show. All right. So the first definition, and you may have heard of this definition before, a linear combination of these vectors is just a sum of scalar products. So that's what the words linear combination means. You may have heard this in other classes. It just means that you take a bunch of scalars, multiply them by the vectors, and add them up. One of the things that you do in a class like differential equations is you end up writing general solutions to the differential equation by doing linear combinations of specific vectors that satisfy the equation, as an example. There's lots of different areas where you do linear combinations, but differential equations is one of the more important, not the word I really want to use when I say important. One of the more important places where it pops up, because when you're solving differential equations, you typically get lots of solutions to the equation. For example, if I ask you to find all functions that have a derivative of 3x squared, what do you tell me? What's all the functions that have a derivative of 3x squared? Well, tell me a function that does have a derivative of 3x squared. Let's start there. X cubed has a derivative of 3x squared, right? Okay. Phew! All right, we got there. Okay. But is that the only function? No. I can take x cubed plus any constant, right? Okay. So I get a whole bunch of solutions that give me a whole bunch of functions that give me a derivative of 3x squared. You could also, if I also ask you, tell me a function whose derivative is itself. E to the x. Can you give me another one?
Plus 1.
No.
That doesn't work because the derivative is just e to the x, right?
Oh, it's okay.
What do I have to do? Okay, 3 times e to the x works, good, right? 2 times e to the x works. Negative 15 times e to the x works, right? Any constant times e to the x works. Okay? But the idea behind that, if you're looking at differential equations, I know this isn't a differential equations class, but I want to show you the point. All right, so you're trying to solve this equation, functions whose derivatives are themselves. Right? And you just told me any constant times e to the x works. Well, e to the x is a solution to this equation, so I know that any constant times it will also work. There's some specific things about this equation that tell me that this is what's going to happen. But you could also do another one. I could ask you, this is a little harder. This is what referred to as a first order differential equation. It has e to the x as a solution, and now I know that all solutions look like this. First order because that's the highest derivative that pops up. This is a second order differential equation. You can check that those two are also solutions. Now, there's a lot of theory that goes on in here, but since I know that this is second order and I've got two different solutions, I know that I'm done. That any solution now has to be a constant times the first one plus a constant times the second one. Notice that this is the whole reason why I went through this. This isn't a differential equations lesson, this is a linear combination lesson. These are my two vectors. This is a linear combination of those two vectors. Constant times the first plus constant times the second. Okay. So this is an area where a linear combination pops up, and it also leads into our next discussion here in a second of a whole subspace of solutions that's generated by these two functions. Okay? That's why I wanted to mention it. I know that if you're not taking differential equations, you really don't care, but if you do, or if you are or will be, you might care. But the whole idea of this is, the theory behind it is, I have a second order equation, I know I'm looking for two solutions that are different, and we'll talk in the next section about what I mean by different. These two are really different, so then I know I have all of them by doing a linear combination of them. So there again, there's infinitely many of these ideas. All right, so by the way, this works for any order that I would like to do. Yeah, Megan?
I'm just making sure, does that say I is equal to h dot 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 n?
That's 1. It's a 1, yeah. Because my subscripts go from 1 to n. And I got a C1, a C2.
Oh, that's a C1.
Yeah. All right. So, what we care about for linear combinations is the idea of creating a subspace. So as another definition, let's let x1, x2, out to xn be in V, then the span of these vectors does this book use a notation? Yes, it does. Okay. Just want to make sure that I'm using the right notation. And the span of this set of vectors is the set of all linear combinations of the vectors. When we're doing the span of a set of vectors, the set of vectors that we start with is fixed. We don't change the vectors. What it's allowed to be changing here are the constants that we're using. Okay? What's true is that if I take any set of vectors from V, I'm just going to call it S, then the span of that set of vectors is always a subspace. Why? I want a subspace every time. The span of a set of vectors is always a subspace, no matter what. Remember again, I said when you're talking about a set of, or doing the span of a set of vectors, the vectors are fixed. You don't get to change it. You get to change the constants, but you don't get to change the vectors that you're using. So if I take a linear combination of x1 to xn and add it to another linear combination of x1 to xn, I get another linear combination. of x1 to xn. The reason for that is, instead of writing out all the details, just to show you what would work, if you've got c1 x1 plus c2 x2, then I wanted to add it to d1 x1 plus d2 x2. What are you going to end up with? Good. Are these first two a linear combination of x1 and x2? Yeah. Is this a linear combination of x1 and x2? Yeah. That's the definition, right? It's just constants times the vectors added together, correct? And the same thing would work for constant multiples. I know I only did this, I didn't do this generally. I didn't do it for a list of n vectors, right? But the proof would be the same. I would just need to add on, at the end here, I would just need to do dot, 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 cn, xn, and so on, right? The proof would be the same to show that it's closed under addition. We agree? You see how that would go, yes? Yeah. Okay. So, the fact that the span is a subspace of V isn't really a surprise, because if I add linear combinations, I get a linear combination. If I take a scalar times a linear combination, I get a linear combination. Okay. All right, so we've already talked about this as well when we were doing things with solving systems of equations, even though we didn't call it this. Let's say you had a matrix that represented a homogeneous system of equations, and this was the reduced row echelon form. How can we write the solutions of this homogeneous equation? We did this last, well, it's been a while, I suppose, but we did this a while ago. How can you write the solutions to this system? So this, what does this equation tell me? Well, let's do this one. What does this equation tell me? Okay. Good. And the first one tells me? Good. So that was the two equations, right? And then what did we look for when we were writing the solutions? The free variables, correct? Where do we have free variables? The second column and fourth column. So we can represent x2 with an S and x4 with a T. Right? So what is x3 then? Good. And what's x1? And then if we split this up into vectors, we talked about this before too, right? Split it up into two pieces. If I want to write it as vectors, if we have x1, x2, x3, x4, how can I write that if I split it into pieces with vectors? We have an S times something and a T times something. Right? Good. Good. Excellent. Why did I mention this particular example in the middle of talking about spans and linear combinations? Is this a linear combination? Yeah. So it looks like I've got two specific solutions to the homogeneous equation system, right? if you check, these two certainly satisfy both of those equations, don't they? And now any linear combination satisfies this as well. That was the whole point of this. So what we notice is that, I will just write this down, the solution to this system can be written as a span. It's the span of these two vectors. Now we're writing it as columns, but the solution to that homogeneous system can be written as a span of those particular vectors. Notice that this is a subspace. What's the bigger space where these solutions live, by the way? How many components do each of these vectors have? How many different components do the vectors have? 4, so where do they live? Or where do you think of them living? And yeah, R4, right? Because all of their entries are real. All the components of the vectors are real. So this would be a subspace of R4. Notice also that was how many variables we started with, which corresponds to the number of columns we have. All right? These are things we're going to talk about later. That's why I'm pointing them out. Okay. So this is a subspace of R4, and again, that corresponded to how many columns we had in our matrix. So another fact that pops up along with this is that the set of solutions to AX equals 0 to a homogeneous system where A is an m by n matrix is a subspace of Rn. This particular subspace has a special name that we'll talk about it's going to be a while. 5.6, I think. Yeah, 6 or 5.5. It's not hard to check that this is a subspace. If we do this really quickly, just to show you, let's suppose that x and y are solutions to this equation. I'll do the addition. You should be able to do the scalar multiplication so that I have 1 minute. I need to show that if x and y are solutions, we need to also show that x plus y is a solution, correct? So that means when I plug it into the equation, it has to work. So if I take a times x plus y, what can I do with the multiplication? Distribute it? And what are we assuming about x and y? They're solutions to this equation up here, right? So if they're solutions, what do each of these equal? 0. So we get x plus y is also a solution. Like I said, you should be able, that's one piece of being a subspace, right? Showing that it's closed under addition. You should be able to do the scalar multiplication. It's very, very similar. All right? So we'll talk a little bit more about spanning sets next time, as well as get into section 5.3. I'm going to post a video for 5.3. So I'll email everybody when that's done, and I want you to watch that for Wednesday.